All right, kids. So what we're going to do today, we're going to do a bunch of practice problem to make sure you're getting everything down. So the next thing we're going to do, I'm going to do a calculation with this, how to calculate the concentration at equilibrium. Now, here's the equation we have. And again, I'm just going to go over it one more time. I want to make sure you really get the concept down. Some reaction, they don't go to completion. This is an example. It has a forward reaction, it has a backward reaction. At the beginning, you have a lot of A. You have all A at the beginning. So at the beginning, you have mostly product. So the rate of going forward is going to be faster. This reaction is going to go forward. Now, as you're forming more and more B, then this reaction also starts to go backward. And this back and forth is going to keep going until you reach equilibrium, until you are in equilibrium, until you reach a stable state, right? So you're just going to keep going until you reach stable state. Now, in that stable place, basically what that means is the rate of going forward and backward are equal. Now, that does not mean you have 50-50. No. It means they are going to reach a state where the ratio of these two is not going to change anymore. If the ratio is 40-60, it's just going to remain. When it gets to that stage, that's just going to remain. So then the number of A going to B and B going to A is going to remain the same. That ratio is going to remain the same. That means we are in equilibrium. So far, so good. And every time you have an equilibrium equation, don't forget, you have an equilibrium constant. And equilibrium constant is temperature dependent. It does not have a unit and is product over reactant. And the magnitude of the equilibrium constant will tell you at equilibrium, when you're in equilibrium, which one you have more. If the equilibrium constant is large, that means what? Because equilibrium constant is product over reactant. If this is large, that means you have more product. If this is small, that means you have more reactant when you are at equilibrium. We're good? Okay. So, here's the first problem. What is the concentration of A at equilibrium if we start with 0.0500 molar in A? Alright, now how are we going to do this? So they tell us the starting point. This is how much we have at the beginning, okay? And then they're going to ask us, what is the concentration at equilibrium? And we have our equilibrium constant. The way we do this, we form an ice table. Okay? We form an ice table. Sometimes I call it icy because it sounds cooler, but it's ice table. Now, I means initial. Okay? So I means initial. C means change, and E means equilibrium. Okay, initial, change, equilibrium. So every time you're doing this kind of question, every time you're calculating concentration at equilibrium, you do an ice table. Ice table. All right, initial. At the beginning, I have 0.500 molar of A, and at the beginning I have no product. Now what's the change? The change is going to be A is going to go away over time, and I'm going to form B, okay? Minus X because A is going to go away over time, and I'm going to form B. So far so good, which means at equilibrium it would be 0.500 minus X, and then X. Okay, so I start with A. I don't have any B at the beginning. And then what is the change? Sum of the A, X amount of A is going to go away, and X amount of B is going to be formed. X amount of A is going to go away, X amount of B is going to be formed. So at equilibrium, it's 0.500 minus X, and then this would be X. So far, so good. Okay, that's our ice table. Now, we have, then the next thing you're going to do, you're going to write down the equilibrium constant. And the equilibrium constant K is product over reactant. So it would be concentration of B to the power of 1 over concentration of A to the power of 1. So far so good. Equal. Okay, now check over here. At equilibrium, B is going to be X. At equilibrium, B is going to be X. And at equilibrium, A is going to be 0.500 minus X. Hopefully you're still following me. Yeah, so at equilibrium, you have our K. B is going to be X. And A is going to be minus 500 minus X. And our equilibrium constant is 1.22. So that's what's going to equal 2. You guys are good so far? Okay. Now, let's go over the math together too. And I know you know it. So, what are we going to do? This would be X equal. You have to multiply this out, right? 1.22 times 0.500 minus X. Okay. That would be X equal. I'm going to multiply this out. 1.22 times 0.500. It would be 0.610 and then minus 1.22x. Okay. Now what I'm going to do, I'm going to move all the x to one side. So I'm going to move this one to the other side. If I do that, then I end up getting 2.22x, right? Because this is 1x, and then I'm going to move this to the other side. So it'll be 1x plus 1.22x, and then equals 0.610. I know you know all of this. I just want to make sure. And then x is going to be 0.610 over 2.22. And what I'm going to get for x, I'm going to get 0.275 molar, right? Those are all molarity. Okay, beautiful. So we got x. Now, if I get x, I said, what are the concentration of A at equilibrium if we start with that? So, at equilibrium, so we did the math. So now, at equilibrium, the concentration of A is going to be what? Remember, at equilibrium is 0.500 minus x, right? And I just have my x. So at equilibrium is just going to be 0.500 minus x, and my x is 0.275. So what I end up getting is 0.225 molar. Is that. Now at equilibrium, also let's take it to the next level. What would be the concentration of B? B is just x, right? B is just x. So concentration of B would just be 0.275 molar. Yeah? Okay, this is the first time we do an ice table. So every time you're trying to figure out the concentration at equilibrium, you do an ice table. Initial change in equilibrium, and then equal it to the K constant. We're going to do a bunch of these problems to make sure you get it down. Yeah, ready for next one? Let's do next one. I know I probably bore you with all the math, but I just wanted to make sure I go over every step. All right, here's our next one. What is the equilibrium concentration of NO2 if we start with 0.490 molar N2O4? Okay, do me a favor. We've done one problem. I think you can do this. Pause me, do this, and then unpause me. We're going to go over it together. So hopefully you go. I'm trying to figure out equilibrium concentration. I'm going to use ice. This kind of sounds cool. I'm going to use an ice table. What is the initial? Initially, we have 0.490 molar. You have to plug in molarity to this ice table. 0.490 molar N2O4, and I don't have any of this. Now, over time, what happened? Over time, the N2O4 is going to go away. I don't know how much. And then some NO2 is going to form. But I need you to pay attention to this. When one N2O4 goes away, how many NO2 is going to form? 2. You have to care about the mole ratio, right? Because when one of these goes away, 2 of these is going to form. Don't forget that the mole ratio matters. So at equilibrium, we're going to have 0.490 minus x, and we're going to have 2x. So far, so good. Okay. So now we know what is the change, what's going to be happening at equilibrium. Now I'm going to equal this to my equilibrium constant. So my K is going to equal product over reactant. My product is NO2 to the power of 2 over N2O4 just to the power of 1. You guys are following me so far? Now, NO2 at equilibrium is going to be 2x, okay? Again, to the power of 2, because basically 2x is a concentration of NO2, right? 2x is a concentration of NO2, and then I have to do it to the power of 2. Over, what is the concentration of N2O2 at equilibrium? It would be 0.490 minus x, and then we're going to equal it to 0.00463 equilibrium constant that is given to you. Yeah? Not bad, right? So let's go over it one more time. I'm trying to figure out equilibrium concentration. I do an ice table. Initially, I have this, none of that. Over time, this is going to go away. I don't know how much of it. And then for every N2O4 that goes away, 2 NO2 is going to form. So minus x and then 2x. And this will be my equilibrium concentration. Equilibrium constant is product over reactant, but you also have to care about the stoichiometric mole ratio, right? Now, I know NO2 at equilibrium is 2x, so I'm just going to put 2x for that. Don't change the formula. I still have to do it to the power of 2. And then the concentration of N2O4 is this one. I'll plug it in, equals the K equilibrium. Okay, now, this math is not easy, right? This math is not easy. Because if you multiply everything out, how would you be able to actually do this math? What do you guys think? I want you to look at this. How would you be able? Because you have x squared, you have x. What do you need to do to be able to solve this problem? What do you guys think? Think back about your algebra days. What do you guys think? You need quadratic equation. You need quadratic equation to do that. So let me put it up. Here's a formula for quadratic equation. Probably you remembering things, right? I'm actually going to do an example of quadratic equation with you. And then to kind of remind you what a quadratic equation was, and then when we use it, okay? Now, quadratic equation was when you had, I'm just going to make up an example. When you had, for example, trying to figure out this problem, x squared minus 380x plus 2,197 equals 0, okay? So this is a format that you would have for the quadratic equation. Again, this is relevant because when you look over here, that's what's going to happen. I'm going to have x squared. When I multiply this out, I'm going to have x and I'm going to have a number. So I have x squared, x, and a number. Again, I'm not doing this one. I'm just doing a different one. That one, I leave it to you to figure it out. But I want to do one example so you know what the quadratic equation. Okay, so this is my quadratic equation, is when I have a format that is x squared and an x and a number. Now, in this case, A would be, this would be A, this would be B, and this would be C. Okay, so my A would be 1 because it's just 1 x squared. My b would be negative 380, and my c would be 2197. You guys are good so far? Okay, now what we're going to do, we are going to plug it in here. So x is going to equal minus b. What is my b? Negative 380. So it would be negative 380 is my b, plus minus b squared. So minus 380 to the power of 2 minus 4. A is my 1. C is 2197 over, okay, 2a. A is my 1. So 2 times 1. So far so good. Alright, x is going to equal. I have, oh shoot, I forgot to put a minus here, right? Because it's minus b, and then 380 is my b. You guys all follow that? I didn't lose anyone? Okay. Now, if you look over here, negative times negative would be positive, right? So I'm going to have a positive 380 plus minus, and if I do everything under this, it would be 135,612 over 2 times 1 is just 2. Okay? And then if I do 380 divided by 2, okay, I get 190 plus minus 184. Okay? So the 190 was 380 divided by 2. So far so good? Okay. So the x is going to be 190 plus or minus 184. So this was a quadratic equation. You do a quadratic equation when you have this format. X squared minus some x, and then it could be plus 2. So basically x squared and then x, and then you have another number. So this was quadratic equation. Hopefully you kind of remember the algebra. Now it's going to go back here. So you have to do quadratic equation for this one also, because you can see the format is going to be the same. Except, luckily for you, your teacher does not like math whatsoever. So here is another thing. When you look at k is a small number, right? K is less than 1. So if k is less than 1, that means we know not much product is going to be formed, right? So what we're going to do, we are actually going to, you ready for this? You're going to love this. We are going to assume this x is 0. We're going to assume this x is 0. And I'll tell you in a little bit later exactly why we can do that. But kc is really small. It's less than 1. We know that not much product is going to be formed probably. So I'm going to assume this is 0. I'm going to assume this x is 0. And on my exam, 90% of the time, 99%, you can assume that this x is 0, because I want to make the math simpler for you. So then this problem is no problem, right? If we assume that is 0, then what we're going to end up with, we would have, let's do this one together, 4x to the power of 2 over, right? Because remember, I have 2 to the power of 2 and x to the power of 2. This has to be multiplied out over 0.490 equal 0.00463. Okay? Now, this is not bad. This is not bad at all. I can easily do this one, right? This is not bad at all. So all I have to do, I would have to take square root of 0.00463 times 0.490 over 2. And that would give me x, right? Again, I'll make sure I didn't lose anyone. So 0.490 times the k, right? And then divided by 4. And all I have to do is take a square root of it. So now it's not bad, right? The math has just got so much easier. And if I do, I get 0.0238 molar. That's going to be my x. That's going to be my x. All right. So, the ice table, you got it down. When you got here, you go, oh crap, I have to do a quadratic equation. Except, luckily for you, I don't like math. So, but you could also assume that this x is 0. And if you assume that x is 0, that just made your math so much easier. Now, why can we assume that? And was it right to assume that? Yes, it was right to assume that, and here's why. So the x is 0.038 molar, right? Right. So I started with 0.49, right? I started with 0.49 molar and 0.0238 molar disappeared, right? Will form into product. If I do this, if I try to get the ratio, this would be 4.8%. So the change is less than 10%. When this change is less than 10%, it's okay to assume this is 0 and approximate it. I want to explain this one more time. So to avoid a quadratic equation and a huge headache, we assumed this x was 0. And I did that because when I was looking at this problem, I go, this k is really small. When the k is less than 1 and the k is really small, that means not much product is going to be forming. So I can do approximate and I should be okay. Now, if you want to double check at the end that what you did was right, so you figured out x, you figured out the change, right? The change was 0.0238 molar. We started with 0.490. So this is what we end up with, this is what goes away, this is what we start with, times 100, that would be 4.8% of it is going that's the change. The change is 4.8%, right? 4.8% of N2O4 is going to form into product. Now, that's less than 10%. If that's less than 10%, so we're okay approximately this and not using a quadratic equation. Yeah? Okay. Now, let's go to our problem. Our problem was, what is the equilibrium constant of NO2? What is the equilibrium constant of NO2? Okay, so we have X, right? We have X. Now we want to know what is the equilibrium constant of NO2. What would be the equilibrium constant of NO2? We know X, and at equilibrium, NO2 is 2 times X. Do you agree? At equilibrium, NO2 is 2 times X. So we have the X. The X is, so it'll be 2 times 0.0238 molar. That would give me the NO2 concentration. Yeah, you guys got this down? Okay, nice job. And let me finish it. So this would be 0.04776 molar. That would be the equilibrium concentration of NO2, and that's what the question asks you for. Again, why is 2 times? Because at equilibrium is 2x. Because for every x that goes away, 2x is going to be formed. Yeah? Okay, does this one make sense? Yeah, hopefully, no, I can't hear you, but hopefully you're telling me that it does make sense. Because this much went away, that's my x, and this is what I started with, so very small amount actually form into product, so it was okay to assume that this x is 0. It was okay to assume that. Okay, you know what we're going to do next? We need to do more practice problems. You ready for that? So most of the time you don't have to do this, especially on the exam. I'm not going to ask you to do this. So you can, but I want you to know how to do this. So if I ask you for the homework or for the quizzes to do this, you know how to do it. All right, we start a reaction with 0.325 molar A and 0.483 molar B. What will be the equilibrium concentration of A and B? Are you ready for this? Okay. So I ask you what's going to be the equilibrium concentration. That means you have to use what? You have to use ice. That means we have to use ice, yeah? Okay. At the beginning, how much A I have? At the beginning, I have 0.325 molar A, but I also have some B at the beginning. Oh, interesting. We haven't that before. Now we do. So we also have some B at the beginning. You following me? So at the beginning, I have this and I have that. Okay. So far, so good. Now, what's going to be my change? My change is going to be minus x, and my change is going to be x. So at equilibrium, it will be 0.325 minus x and 0.483 plus x. But hold on a second. Here's the question. How do I know that this is going to be minus x and this is going to be x? Here, that was obvious because I had nothing but the reactant at the beginning and I had zero product. So the only option was that this would go away and some of the product is going to form. But in this problem, I have both. So how do I know that it's going to be minus x and x? Or do I know? Well, here's how you would know. We could figure out, first we need to figure out, are we at equilibrium, how far away we are at equilibrium, and what do we need to reach equilibrium. Now, what did you use? We talked about this last time. If you want to know if you're at equilibrium or not, and if you want to know how you can reach equilibrium, what do you need to use? You need to figure out Q. Do you agree? You need to figure out Q. Q is the same thing as K, concentration of product over the concentration of reactant. And in this case, my B was 0.483 over my A is 0.325. Okay, you guys are following me so far? Okay, that's pretty good. So if we do this, let me see, where is my paper? What is going to be Q? Q is going to be 1.49. Okay. Now, K over here is 1.22. So, here's Q, here's K. What can you tell me about Q versus K? Q is bigger than K. We talked about this last time. Tell me you remember it. Impress me. I'm always impressed by you guys. So Q is bigger than K. What does that mean? That means we're not at equilibrium, okay? And how can we reach equilibrium? If you have Q is larger than K, if Q is larger than K, remember, it's product over reactant. If Q is larger, that means I have too much product. That means I have too much product. Do you agree with that? So when you have a large Q, that means you have, because the higher the B, that will be the higher the Q. That if I have a larger Q than K, that means I have too much product. Now, if you have too much product, what do you need to happen for you to reach equilibrium? I have too much product, so it has to shift what? It has to shift to the reactant to reach equilibrium, right? it has to shift to the opposite side. It have to basically go back. So I would have to make some reactant in order to reach equilibrium. You guys got that? So again, this is too much product. If I have too much product, that means the reaction has to shift to the left. It has to shift to the reactant. So I need to form more reactant to reach this number. This has to go up. A has to go up in order for me to reach 1.22. And 1.22 is equilibrium, is my stable state. Yeah? Okay. So based on that, what needs to go away? Product needs to go away. So I have minus x and I have x. Product needs to go away. Now, before you get confused, again, this problem or the problem before that, those were easy because you have nothing at the beginning but reactant. The only option was reactant forming into the product until you reach equilibrium. The same as here. I had all reactant and nothing product. So it was obvious which way it was going to go. But in this problem, I have both A and both B. Then you need to figure out, where are you? We know we're not at equilibrium here. We have too much product. To reach equilibrium, I have to have more reactant, right? To get to this number, A has to go up. So I'm shifting to the reactant. So I need this going to be minus x. This has to go away. And then x needs to be forming. You guys got that down? Okay, I know this is... We've actually done almost every type of problem today. That's good. Yeah? Okay. So now we have our ice table, and then now we're good. So we know that K is product over reactant, and K is going to be, oh boy, give me 1 second. This is, I did not just do this, 0.483 minus x. Okay, hopefully you're not confused. So it's going to be product over reactant. My product would be 0.483 minus x at equilibrium. My reactant would be 0.325 plus x at equilibrium, right? Equal. And then my Kc is 1.22. My Kc is 1.22. Okay, not too bad, right? Not too bad at all. We completely got this. Let's go over the math together anyway though. So then it's going to be 1.22 times 0.325 plus x, right? I'm multiplying this out together, equal 0.483 minus x, okay? Now I'm going to multiply this out. You have to multiply that out. So that would be 1.22 times 0.325. That would give me 0.397 plus 1.22x. Okay? That's going to equal 0.483 minus x. Alright, I'm going to move things around so all the x's are on one side. What that means is this minus x is going to go over here. So it's going to become plus x. So it will be 1.22x plus 1x. And this 0.397, I'm going to move it to the other side. So I end up getting 2.22x equal 0.483 minus 0.397. Alright, if I clean it up, x is going to equal, and this would be 0.086 when I subtract those two together. X is going to be 0.086 over 2.22, and that means I get 0.039 molar. Beautiful. That is my x, okay? So I just got the x. Okay, so now that I have the x, I can figure out what happens to what are the concentration at equilibrium. So the concentration of A at equilibrium and the concentration of B at equilibrium, again, you have the x, all you have to do is subtract them. So for A, it would be 0.325 plus 0.039, and for B it would be 0.483 minus 0.039. How am I getting this from? I'm getting them from here. I'm just plugging this in. So the concentration of A ends up being 0.364, and the concentration B, it would be 0.444. Okay, these are all molarity. Yeah? Okay. We did a lot of practice problem today, and I'm going to stop now. And next time, I'm not going to introduce a new topic actually. I'm just going to do nothing but practice problem with equilibrium to make sure that you get the equilibrium down. But the things that to kind of take a note of from is, again, equilibrium. Don't forget equilibrium constant, product over reactant. Don't forget Q, that you can figure out if you're at equilibrium or how you need to get shifted to reach equilibrium, right? As we had right here. How to get shifted to, how to shift to reach equilibrium, and then to figure out equilibrium concentration. Don't forget we have to do ice table. And that's pretty much it. Alright, so next time we'll do practice problem, and then we move on to the last part of equilibrium. I'll see you guys next time.